Hello, welcome you all. Myself Deepmala Meena, Assistant Professor in Physics, Government College, Kota. In previous video, we have discussed about rigid body dynamics and also rigid body. In today's lecture, we will discuss about the inertial coefficients. This is our second lecture regarding dynamics of rigid bodies. So let me start with inertial coefficients. As we know that if a body is at rest or moving with a constant velocity, then in order to change its state, external force has to be applied on the rigid body. This is for translational motion of the body, and this property is known as inertia. Similarly, if body is at rest or moving with constant angular velocity, then in order to change its rotating state, we have to apply external torque on the rigid body. This property of the body is called rotational inertia. Rotational inertia of the body is measured in terms of a physical quantity known as moment of inertia. The more the moment of inertia, more the torque will be required to change the state of the body. So, we are taking that if in translational motion, we are having the property of inertia for which greater the mass, greater the force will be applied. Similarly, in rotational motion, we use torque and moment of inertia. More the moment of inertia, more torque will be required to change the state of the body. So, the physical significance of moment of inertia of rotating body is the same as the mass of the body in translational motion. Okay, in translational motion we are having mass, and in rotational motion we are having moment of inertia. Okay, inertia depends on the mass of the body in the translational motion, and moment of inertia depends on the mass of the body as well as the axis of rotation about which the body rotates, and distribution of mass with respect to axis of rotation. Now we will discuss its mathematical form. The total angular momentum of a body, we know total angular momentum is J equals to R cross P. If we are having the system of n particles, and this is the position vector for ith particle, momentum of ith particle, so we can take the total angular momentum with the summation of this term. So total angular momentum is I equals to 1 to n ri cross pi. As we know, p equals to mv, momentum equals to mv, so we can write in pi equals to mivi for ith particle. And also we know the linear velocity of ith particle with relating omega. We can write it vi equals to omega cross ri. Ri is the position vector of ith particle and vi is the velocity of ith particle. And this is the relation between the v and r and omega. So by putting the value of vi here, by putting the value of vi omega cross ri, what we get? J equals to mi ri cross omega cross ri in place of vi. Okay, now as we know, according to vector identity, then a cross b cross c equals to b a dot c minus c a dot b. So by putting the value in this term, we get J equals to mi, and solving this, omega ri square b a dot c minus ri dot omega. So by putting the value and using this vector identity, we get the value of j. What is this? J equals to I equals to 1 to n mi omega ri square minus ri dot omega. If we are having xi, yi and zi are the component of ri, and omega x, omega y and omega z are the component of omega, then we have omega equals to I cap omega x plus j cap omega y plus k cap omega z, and also r equals to I xi j yi plus k zi. So by these values we can write ri dot omega because we are having ri dot omega in this equation. So we can simply write this ri dot omega equals to xi omega x plus yi omega y plus zi omega z. So and in component form we can write j as I cap jx plus j cap jy plus k cap kz. Okay, it is clear. Now the equation of j is I equals to 1 to n mi, and this which is from the previous slides. Now we will put the value of ri and this. Okay, so what will the equation? J equals to summation of I equals to 1 to n, this is mi, and omega ri square. So we are writing mi ri square as it is, and this omega in terms of I cap omega x plus j cap omega y plus k cap omega z. This is our first term which we have written in this form. Now for this second term we will have summation of I equals to 1 to n. This is summation of I equals to n mi and the value of ri. This is the value of ri. I cap xi plus j cap yi plus k cap zi, and this is the value of ri dot omega xi omega x plus yi omega y plus zi omega z. On solving this expression we are having the terms j equals to this is term in form of I cap this is our first term, this is our second term, this is okay. Now from this is our third term, and also from the second term we are having this is term of I cap, means summation of I equals to 1 to n mi xi, and multiplying this by is whole expression, this is term I cap. Similarly for the term j cap we will write I equals to 1 to n, this mi, this yi, okay, this is j cap, and multiplying this term by this whole expression, and similarly for z. So we are having this whole terms for the z. Now we will solve in next. Okay, on solving this we get solving the meaning we are having the terms I cap, j cap, k cap, and I cap, j cap, k cap. So we can write this j in the component form jx, which is having unit vector I cap, means this term and this term. Similarly jy, which is in the term of j cap, this term and this term, and similarly for k cap, which is zz, this term and this term. So what will be our expression? Jx will be summation of I equals to 1 to n mi ri minus xi square omega x. We can go back for this here. This is the term for jx. So mi ri square omega x and also mi xi square omega x. So we will have mi and omega x square common from the term, omega x common from the term, and this will be ri square minus xi square, and out of the bracket mi and omega x. Similarly for omega y we are having mi ri square omega y. Here we will have mi ye, this is the term omega y. Okay, so we will write these terms here, and solving this we have jx equals to I equals to 1 to n mi ri square minus xi square omega x, plus here we are taking this sign in bracket I equals to 1 to n mi xi yi omega y, plus minus we are taking this minus in the bracket I equals to 1 to n mi xi zi omega z. We have taken this jx term with this I cap, this term in the jx term, and this whole term will be in the jx. So on taking this term and this term for jx, and this term and this j cap term for jy, and this term and this term for jz, so we get the values of jx, jy and jz. And above this equation can be written in terms of Jx equals to Ixx omega x. This is the value of Ixx and this is omega x. And we can write this term as Ixy omega y plus this is the term Ixz omega z. Similarly for Jy, this is the term we can write Iyx omega x. This term we can write Iyy omega y and this term Iyz omega z. Similarly for Jz, this is Izx omega x, Izy omega y and Izz omega z. So we have summarized these equations in terms of this Ixx, Iyxy, Ixz and similarly for y and z. So we are having simple form of the term and where Ixx is this term, Iyy is this term, Izz this term and similarly all other terms. Now above mentioned coefficients are called inertial coefficients. What are these? These all are 9 coefficients are called inertial coefficients and in the matrix form we can write these Jx, Jy, Zz. Here we are taking omega x, omega y, omega z and these are the 9 inertial coefficients. These 9 elements are components of second rank tensor of inertial coefficients. This tensor is called moment of inertia tensor and this is in the form Ij equals to Iji means here Ixy equals to Iyx, Iyz equals to Izy, Ixz equals to Izx. Hence, moment of inertia tensor is a symmetrical tensor. The diagonal elements of the matrix of the inertial coefficient have a special property. Diagonal elements means we are taking Ixx, Iyy and Izz and from previous section we have Ixx equals to this value, Iyy equals to this value and similarly Izz equals to this value. So what we can write Ixx equals to we have summation of I equals to 1 to n mi ri square minus xi square. As we know ri is the position vector and the value of this is xi square plus y I square plus z I square, right? So by putting the value of ri square we have this term because minus x square plus x square will be cancelled. So we get I equals to 1 to n mi yi square plus zi square. Similarly, we can write for Iyy here y term will be cancelled and remaining terms will be zi square plus xy square, xi square. Similarly, these terms can be written in terms of izz. Okay. So here this term yi square plus zi square is the square of the distance of the ith particle from the x-axis. This is the square of the distance of the ith particle from x-axis. Hence, the product of this with mass mi, this mass mi of ith particle by summing this Ix can be calculated. Okay. This Ixx is called the moment of inertia of rigid body about x-axis. What we have said here, we have written Ixx in terms of this. Similarly, we will write Iyy and we will write Izz. Okay. So this is the square of the distance of ith particle. Okay, from x-axis. And this is the mass of ith particle. So we can say this is the moment of inertia of ith particle. Okay, because we know that moment of inertia I equals to mr square. If we take this for ith particle, then this will be term. Okay, if we will summation, we will take the summation for all the particles. Means we will take I equals to 1 to n and mi yi plus yi square plus zi square. Then this will represent the moment of inertia of the rigid body about x-axis Similarly, the moment of inertia of a whole body about y-axis and about z-axis can be calculated by taking here I and taking here y and that will be the value of I and I. Now, from previous section equation, we have Jx equals to Ixx omega x plus Ixy omega y plus Ixz omega z, and similarly Ijy equals to Iyx omega x plus Iyy omega y plus Iyz omega z, and also for Zz equals to this equation. So, the direction of angular momentum J is not necessarily in the direction of angular velocity of which is omega. So, when Ri not perpendicular to omega, okay? But it is possible that there may be three perpendicular directions for irregular rigid body, for which angular velocity is coincident with the axis of rotation. These axes are called principal axes, and moment of inertia is obtained these axes. In this case, we will have Ixy equals to Iyx and Ixz equals to Izx and Yz equals to Izy. This will be 0. All these six terms will be 0, and we have only the terms of Ixx, Iyy and Izz, and Jx will be Ixx omega x, Zy will be Iyy omega y, and Zz will be Izz omega z. Now we will take one or two example for this. The angular momentum of any body is this. This is the value of angular momentum J. And the rate of rotation is 30 revolution per second. Okay. Now calculate the moment of inertia of a body. Okay. Now we have J equals to I omega. Okay. Equals to I 2 pi n, because we are taking this in the form. So we have to calculate here I. I will be j upon 2 pi n. By putting the value of all these things, we get I equals to 0.5 kg meter square, because I is m r square, m if we take m in kg and r will be in meter. Okay. Now let me take second example. Three particles of same mass m are placed at this position x, y and z coordinate. Like this, first particle, second particle and third particle, and we are taking the mass of these three particles are identical, okay, in a certain system. So now determine all inertial coefficient of the system. So we have to determine the inertial coefficients. Now the location of the particles are showing in the figure. This is in x direction, this is in y direction and this is in z direction. For first particle, this is our first particle, we are having x1 equals to a, y1 z1 0, and second particle x2 equals to 0, y2 equals to a and z2 equals to 0. Similarly for third particle, here is the third particle, x3 equals to 0, y3 equals to 0 and z3 equals to a. So we have Ixx equals to miyi square plus zi square. Okay. So we can put the values of this. We have m, this will be the only value, and we get 2m square. Okay. Similarly, for Iyy, we will have 2m square, and for Izz, we will have 2m square, and all other terms Ixy, Iyx, Iyz, Izy, Izx, Ixz will be 0. So, in the form of this, we have I equals to 2m square in the diagonal form, and all other terms are 0. Okay. Now, thank you.